This is a tutorial on how to use the dd command in Linux. Originally this tutorial was created for CJ4700, which is now cross-listed with IT4100, the File Systems Analysis class. In this class we use dd to locate and extract certain file system structures for analysis. And this video is for anybody who missed class or just anybody who wants to learn how to use dd. dd doesn't actually stand for anything. Depending on what you read, it'll say it stands for different things: data dump, data description, even disk destroy. But essentially it's a command for byte manipulation. It allows you to control the bytes that you're copying and to do selective extraction. It's a very, very versatile tool. The basic usage for the command is a little different than other Linux commands. Usually you give the command and you have a dash and then an option to control how the behavior of the command, and then you might give it a source and a destination. With dd, you issue the command dd space and option equals value, option equals value, option equals value to control how it works. It's not like your basic Linux commands. It really runs more like a script or a program where you're feeding it the options that control its behavior. Let's start with the very basic options, IF and OF. And remember that in Linux, everything is a file. So let me pull the command line up here. Okay, I'm just in a temporary folder. And this is actually a Mac terminal, but it'll work just the same. The first thing I want to do is create a file to work with. So I'm just going to use the echo command to do that. So I'm going to echo meet me at midnight by the old oak. Okay. And if I hit enter right now, it's just going to send that information to std out. It's going to send it right back to the screen. So I'm going to hit the up arrow to bring the command back, and then I'm going to redirect that information into file 1. I'm not going to give it an extension because in Linux it doesn't really matter as much. And but I'm going to do a quick ls right there, and you see that it is. I have now created a file called file 1. So I'm going to clear the screen. So I'm going to use the IF and the OF command, or options. So dd space IF equals file 1, OF equals file 2. And that's all I'm going to do. The IF stands for input file, the OF stands for output file. Keep in mind that everything in Linux is a file, so we can actually set IF equal to a disk or a file or a lot of other things. So one record in, one record out, and 36 bytes transferred. So this is telling us everything went just fine. So I'm going to do an ls, and you see there's now a file 1 and a file 2. I'm going to cat file 1. Yeah, that'll send the contents to std out for me. Meet me at midnight by the old oak. I'll cat file 2, and you'll see that it says exactly the same thing. There's really no difference in using dd like this, with the IF and OF being files, and doing CP, file 1, well, I'm going to make a file 3 now. Let's do an ls, cat file 3, the same thing. There's really no difference in using copy and using dd in this way. It's kind of a waste of using dd at this point, but it does demonstrate the very basic function. The IF is the input file, and the OF is the output file. Now, since everything in Linux is a file, we could also do some crazy things with disks. You have to know what the designation is for the disk, and that's going to be in the dev folder. And that's where all the block devices are kept. Now, if this was Linux, let me just adjust the screen here a little bit. If this was Linux, then I would expect to see things like SDA, SDA1, SDB, and so on. And the letter tells you the actual physical device, and the number indicates the partition. But since I'm doing this on my Mac, what I'm actually going to see is, instead of SDA and such, I'm going to see disk. So, oops, let me list everything in the dev folder that starts with the word disk. And you'll see on my Mac, I have one physical disk as designated by the number. If I had two, there would be a disk 0 and a disk 1. And then the S1, S2, and S3 show me that I have 3 partitions on this disk. So I could also use DD, because everything's a file, to duplicate disks. So if I connected an external disk that was at the same size, I could do something like this. IF equals /dev/ disk 0, and then send that information off to another disk that I have attached. So if there was, for example, there was a disk 1, and that would actually move every bit of disk 0 onto disk 1. Of course, they would need to be the same size for it to duplicate properly and everything, but that's how we make a disk-to-disk physical image. I could also just say something like image.dd, and that would actually take all the bits, the physical disk, and put it into a file for me, something that we do in digital forensics a lot. We could also change this to represent a single partition and put those bits into a file. Or we could take one partition and actually write it to another if we'd like. So if I had a disk 1, S1, then I could duplicate just that single partition. DD lets us move bits around. It doesn't care if it's a file, if we're referring to a block device, a physical disk, a partition. It doesn't really care. It will just move whatever bits that we tell it to move around. So let's add some more information here. Let's add another option. And the next option that I want to talk about is BS. You can set a block size whenever you're moving bits around. And the way that I describe this in class is if I have a pile of jelly beans on one side of the room and I want to move that pile of jelly beans to the other side of the room, I have a couple different options. I could go pick one jelly bean up from one pile and walk it across to the other side of the room and drop it off, and then go back and get another jelly bean and walk it across and drop it off, and so on and so forth. And that would eventually move the pile of jelly beans, but it would be very inefficient. Well, another option is I could move 2 jelly beans at a time, or 3 jelly beans, or just go get a whole handful of jelly beans and move them from one side of the room to the other. The more jelly beans that I tote at one particular time, the quicker I'm going to be able to move that pile. Unless I try to move too many at the same time, and then I'm going to start losing jelly beans as I go across the room. So it's the same thing with block size and DD. The smaller the number, the slower it's going to work. In this case, what's happening is it's moving the bytes from the disk up to RAM, and then from RAM down to somewhere else. And the more that I move at a time, the more efficient and the quicker that I'll be, until I get to the point where I'm trying to move too much, until the size of my BS exceeds what I have available in RAM to move around. So for the computers in the lab, about 1 megabyte tends to be a good happy number to move. That seems to speed things up, and is pretty efficient. So normally, by default, BS is set to 512 bytes, because that's a set of a sector. That's the size of a sector, excuse me. But we can adjust for speed, or if we're trying to target specific structures. For example, we'll learn that MFT structures, master file table structures inside of NTFS, are 1024 bytes long. So we can set our BS equal to 1024 bytes as we're looking through the MFT, and we'll be looking at one record at a time. So there's some other reasons to set it as well. Now, BS controls all the other options that are moving, that are referring to blocks. Count is the next option that we're going to play with, and count controls the number of block sizes, the number of blocks that we're going to move before we stop the process. Just remember that BS sets the block size, count determines the number of blocks. So adjusting these two numbers drastically changes how DD is going to work. For example, here's some examples. I would encourage you to pause the video for a second and see if you can figure out what each one of these is going to do, and then unpause again and I'll give you the answer. Okay. All right, so number one, dd if equals file1, of equals file2, and count equals 4 is going to move bits from file1 into file2, or bytes rather, and it's going to move 4. Okay, for what? Well, I said earlier the default size for block size is 512. So this is going to move 2048 bytes from file 1 to file 2. 4 times 512 is 2048. Okay, see the second one here. It's going to move bytes from file 1 to file 2. Okay, now block size equals 1. You might be tempted to think that means 1 bit, but it doesn't. It means 1 byte. And count equals 1. So all this is going to do is move 1 byte from file 1 to file 2. Let's see this next one here. It's going to move from file 1 to file 2, and the block size is 1M. Remember the abbreviations from before, and you can man dd just to make sure, and that will tell you the abbreviations on your version of Linux, but this is pretty typical. Capital M is 1 megabyte. So this is going to move 1 meg. Well, actually, count is not set in this one. So if count isn't set, then it just goes to the end of the file. So it's going to move all bytes from file 1 into file 2, and it's going to move them in 1 megabyte chunks. So it's going to move all of file 1 into file 2, and it's going to move it in 1 megabyte chunks. Something else that you should note is that if file 2 exists, then it will be overwritten. All right, so this last one, it's going to move bytes from file 1 to file 2. It's going to move them in 1 megabyte chunks, and it's going to move 5 of those 1 megabyte chunks. So it's going to move 5 megabytes from file 1 into file 2. If file 2 exists, it will overwrite it. All right, let's demonstrate this at the command line. So I have file 1, file 2, and file 3 that are all the same right now. I'm going to cat file 1, and let's see, let's move the words meet me and put them in file 3. I want to show you that file 3 is completely destroyed, and I want to show you how you can select just part of a file. This, you may be wondering why you're doing that. We don't use dd with text files like this very often, or actually I don't use it at all. I'm just doing this right now to demonstrate how things are moved from one place to the other. Now, if I run xxd on file 1, you'll notice that whenever we create a file using echo, 1 byte equals 1 character because it's just storing things in ASCII. In fact, if I pull up an ASCII table, tell you what, I'll pause and go do that. Okay, so I just pulled up, I just Googled ASCII table and pulled up an image here. You'll see that 4D is the equivalent of a capital M, and 6.5 is the equivalent of a capital A. That can't be right. It should be lowercase e. It is 6.5. I was looking in the wrong column. So XXD is basically just a program that creates a hex dump of a file, and I'm using it right now to show you that whenever you create a file with echo, there's no header, there's no footer. Basically, it just takes the ASCII values for that text and stores it into a file. So if I want to move 1 character at a time, all I need to do is set my block size equal to 1. So I'm going to create an input. I'm going to use file 1 as my input. And I said we were going to write over file 3. I'm going to set my BS equal to 1. That's going to be 1 byte at a time. And since this file is in ASCII, 1 byte is 1 character. So that's also the same thing as saying moving 1 character at a time. And then let's see. I said we were going to select meet me. So I'm going to have to set a count. And let's see, so that's an M, 1, 2, 3, 4. The space counts, that's a 20. That's a hex value of 20, ASCII code 20. So 1, 2, 3, 4, 5, 6, 7. So that's actually a count of 7. You know what, for demonstration purposes, I'm going to move 8 instead because I want to show you something here in just a second. So that would mean it's going to get meet space, me space. It's going to get that other space. All right, so the dd command I wrote uses file 1 as input, file 3 as output. It's moving 1 byte at a time, and it's going to move 8 bytes, which should be the equivalent of MEET space, ME space. Okay, I'm going to run that. Okay, 8 records in, 8 records out, 8 bytes at a time. Okay, we're good to go. Clear the screen here. Do an ls. We have file 1, file 2, and file 3. I'm going to cat file 1. You see it's just the same. And I'm going to cat file 3. And now it says meet me. And it didn't move a carriage return, so my terminals are bumped right up there next to the space. So it destroyed file 3, the rest of file 3, and it moved 8 bytes. Clear the screen here. Pull that command up. It overwrote file 3 with the new information. It moved 8 bytes of that information. So let me just demonstrate something else here. I usually ask this as a test question. If I change, if I were to change BS equal to 2, then what would count be? So before it was 8, but now I'm moving 2 bytes at a time instead of 1 byte at a time. So I just need to divide by 2. So now I'm going to move 4 blocks, and my block size is 2 bytes, which means I'm still moving 8 bytes. For demonstration purposes, let me change this to file 4. BS equals 2, count equals 4. Okay. So now it says 4 records in because it's 4 blocks this time, and all the blocks were successful, and it was 8 bytes. So the number of bytes transferred was the same. The number of blocks changed because we changed the block size and the count. So I'm going to cat file 4, and you'll see that it says the same thing. Okay. So DD is a lot more versatile, and one of the things that makes it versatile is that you can target in your input or your output. To target within your input, you use the option skip. This controls how far into the input that you begin reading before you start moving bytes. BS controls skip as well. Everything is in terms of blocks. So whatever you set skip to is a certain number of blocks. So for example, let's see, DD. So I'm reading from file 1, I'm writing to file 2, I'm moving 1 byte at a time. I'm going to move 4 of those bytes, but before I start moving anything, I'm going to skip 3 blocks in my input file. So I'm going to move 4 bytes from file 1 to file 2, but I'm not going to start copying bytes from file 1 until after 3 bytes. All right. So there's also seek. Skip moves within the input. Seek moves within the output. The way that I remember that is that skip has an I, and I think, okay, well, I pretend like that I in skip stands for input. Just a little way that I use to remember which is which. So skip moves within the input, seek moves within the output. It controls how far into the output you go before you start writing anything. And you're still counting in blocks. So here are 4 examples. So pause the video for a second. See if you can figure out what each one of these do, and then start the video back up. Okay. Line 1, I'm moving bytes from file 1 into file 2. I'm going to move 1 byte at a time. My count is 5, so that means I'm going to move a total of 5 bytes because my block size is 1. Okay. Before I begin to write, I'm going to move. Before I begin to write, I'm going to move 3 bytes into my output file. And before I begin to read from my input file, I'm going to skip 7 bytes. Okay. This next one was actually a trick question. If you look, everything is set the same, and I'm just trying to point out that the options, especially whenever you're dealing with the basic options, the order doesn't matter. You can set the options any way you want, and it'll do the same thing. Okay, the second one, or third one now, I'm going to read from file 1. I'm going to write to file 2. This time I'm writing and reading in 512 byte increments. Now I didn't need that BS at all, actually, since I'm setting it to 512, which is the default value. If I left BS out, this would work just the same. So I'm going to move 512 blocks, or in this case, we could just call them blocks or sectors. And before I begin writing in my output, I'm going to skip over 3 512 byte blocks, in my output, because that's seek. So I'm not going to start writing in file 2 until 3 sectors in. Okay, this last one, same deal. I'm reading from file 1, I'm writing to file 2. This time I'm moving in 1 megabyte chunks. I'm going to move 2 of those 1 megabyte chunks. So I'm going to move a total of 2 megabytes. But before I start reading from my input file, I'm going to skip 3 megabytes in. All right, pretty simple. Okay, switching to the terminal here for demonstration. Let's see, I'm going to do an ls. So I have file 1, file 2. I'm going to remind myself what these files are. File 1 we never really changed. Okay, and file 2 I think is the same thing. Let's see, file 3 right now just says meet me. Okay, and file 4 is empty. Oh no, it's the same thing as file 3. All right, good. So let's see. Let's do this. First, I'm going to create a file 5, and I want to create it from file 1. Let's say I want to put at midnight in file 5. So I want to copy just at midnight and put that into a file 5. So my input file is going to equal file 1. That's where I want to read from. My output file is going to be file 5. I'm going to create another file. Okay. Now let's see, since I'm moving characters, I'm going to set a BS equal to 1. That'll move 1 character at a time. Since, let's see, then I want to move within my input, so that's going to be skip. Right? So if I want to get at midnight, how many do I need to skip? Well, I need to skip 1, 2, 3, 4, 5, 6, 7, 8. So I want to skip 8 bytes. Okay. Now let's see. If I just want at midnight, then I need to go ahead and set a count as well. So at midnight would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 characters. So I'm going to say 12 and grab that space at the end as well. Okay. So I'm reading from file 1. I'm writing to file 5. I'm reading in 1 block increments. I'm going to skip over 8 before I begin reading. And I'm only going to move a total of 12 bytes. I'm going to hit enter. So I move 12 records, which is 12 bytes because block size is set to 1 and count is equal to 12. I'm going to do an ls. Use a file 5. It's been created. I'm going to cat file 5, and you see it says at midnight. So I grab just at midnight. So now the other demonstration I usually do is, let's see, so I'm going to cat file 3 again, and it says meet me. Okay, now I'm going to cat file 1. So let's say I want to fix it. Let's say I want to have meet me, and I want to put at midnight by the old oak. So I want to fix the file at this point. So in this case, I'm going to do dd if equals file 1. That's where I'm going to read. That's the one I've never changed. So I'm going to fix file 3. Okay. I'm just going to set BS equal to 1. So I'm moving 1 character at a time. I want to read all of the rest of file 1. If I'm going to fix it, then I'm going to take all of file 1 and put it in file 3. So I'm not going to set a count. If you don't set a count, it just reads to the end of the file. So I need to seek within my output. So my output file 3 is 1, 2, 3, 4, 5, 6, 7, 8. The space there is at 8, so I'm going to seek 8 before I begin writing. So actually, if we really want to do this, I do need to skip within my input, don't I? Because if I'm really going to fix it, then I need to skip over 1, 2, 3, 4, 5, 6, 7, 8. I can skip over 8 as well. I mean, it really wouldn't make a difference because it's the same information. Maybe that's not the best demonstration. But so if I hit enter, do a cat on file 3, and you'll see it's now fixed. The reason it wasn't that great of a demonstration is because this is the same information. This original bytes. But actually, it would look the same if I hadn't have used skip, because meet me was also in file 1. Also, it's worth noting that I could have changed this command. If we had set bs equal to 2, what would skip and count become? Okay, so if I'm moving 2 bytes at a time, then skip could become 4 and count could become 6. How is this useful in the real world? Well, an MBR is the first 512 bytes of a disk. So we could target a disk. Let's see, we could do, let's say the disk is at SDA, and we could save the MBR for analysis, or view it if we would like. Let's see, we could, so if we want just the MBR, which is the first 512 bytes, we don't have to skip anything, and we're creating a new file, so we don't have to seek anything, so we just need to set a count equal to 1. And that would extract just the MBR and save it to a file from /dev/SDA. We'll also use in class, we'll use DD to actually view things. If I get rid of the OF in DD, it will actually send that to the screen, and then we can use pipe, which we talked about in the Linux basics, to send that into a hex editor, and we can actually view the first 512 bytes, which is the MBR, in hex. And I'll say I'm on a Mac terminal right now, so I can look at the first 512 bytes of the disk. Actually, it may not let me. Let's see. It may not have the right permissions to do this. Let's do count equals 1, pipe it to XXD. Yeah, it's denying me permission, but we'll demonstrate this in class. It just creates a hex dump showing the first 512 bytes, and that's one of the things that we'll be doing. You could also, well, we'll talk a little bit about using some of the fake block devices, or the virtual block devices. You can set if equal to /dev random or /dev 0, and actually use it to wipe things, to wipe out sections, and to restore things. So, for example, if I set a count equal to 1 right here, oh, actually, let me create a file. OF equals, let's just call it 0. Let's just do 512 bytes, and let's see. And then I'll do XXD on the file that we just created, and you'll see it just created a file full of zeros. And we could do the same thing with random. So let's just change my OF to, say, random, and set dev equal to random instead of 0. And then let's see, I'll cat the file that we just created. And, oh, not cat. Cat's not meant for random values like that. Clear the screen. And that's XXD on the random file. And it just created a bunch of random binary values in that file. Now, how that's useful or informative, or how we would use that in the real world, is I could set DD input equal to 0, and I could set my output equal to a physical disk, and that would actually wipe out my entire disk. Or I could count equal 1, that would wipe out the first 512 bytes. Or I could skip over and just wipe out a particular section. There's a lot of different ways that we can use it to wipe and destroy disks. All right. So we covered. Let me pause here and pull up all the options. We covered the basic options. DD, IF equals. And let's see, OF equals, BS equals, count, skip, and seek on tests and things. Usually I give you a specific task to complete, and then I'll give you all those options, and you tell me which ones to set and what you should set it to. We'll be using it to zero in on specific areas of the disk by using skip and count, and even BS to look at specific structures. Once we read about where they're actually located, we'll zero in the image and pipe that to XXD so that we can view them as hex dumps, or you can save that out so that you can print it and do your analysis that way. And I hope this was useful to anybody who's wanting to use DD. If you man DD, you'll see that there are more options than just the ones that I've covered here. And different ways to actually use it. Right. Thank you.